Hello everyone, I'm Yijun Li from Beihang University. Today I'll introduce you Transitioning360 Content-Aware Normal Field of View Virtual Camera Passes for 360-degree video playback. Nowadays, 360 cameras and head-mounted displays are becoming popular, which contributes to the increasing number of 360 videos and images on the internet. Because of the low resolution, heavy weight, and high price of head-mounted displays, the majority of users tend to watch 360 video on 2D displays, like personal computers or mobile phones. The left figure shows one of the portable 360 cameras, and the right one shows the experience of watching 360 video on YouTube. In this traditional interaction mode, users usually need to use mouse or touch screen to frequently change the current view content, which is tedious and inconvenient. Other than that, it is easy for users to miss the important objects outside the field of view. To solve this problem, previous work mainly focuses on computing single normal field of view camera paths to track important objects in 360 video automatically. For example, the method paneled to vid densely samples spatial temporal glimpse for every 5 seconds, where each glimpse is rated with a capture worthiness score. Then a virtual camera trajectory is constructed by maximizing the accumulated score. The final normal field of view video is rendered by cropping the view along the path. As for Deep 360 Pilot, it uses an object detector to propose candidate bounding boxes, and uses an RNN-based selector to filter the optimal bounding box. Finally, it uses an RNN-based regressor to learn smooth transitions between selected bounding boxes and renders the final result. These two methods aim to extract single normal field of view video without considering the interaction between users and the 360 video. To support interaction, Kang and Cho proposed an interactive and automatic navigation system computing the camera path in the following 3 steps. Firstly, it calculates an initial path considering pixel-wise saliency and camera smoothness based on optical flow in the scene. Then it performs field of view aware path planning to adjust the view using regional saliency. And finally, it performs temporal smoothing for the path. But the above 3 methods only compute one single camera path for navigation. Users will be unaware of the important objects outside the current field of view. In outside-in methods, the candidate off-screen content is visualized by creating off-screen view thumbnails that are floating on the screen. However, the off-screen content is manually labeled and fixed at constant positions, which does not extend to complex and dynamic scenes. Therefore, we propose Transitioning360, a new technique for 360 video navigation and playback on 2D normal field of view displays. Given a 360 video and the number of normal field of view camera passes, our method computes the camera passes by considering content awareness and diversity and renders the normal field of view content to the thumbnails. Users can switch between them by pressing direction keys or clicking thumbnails. Our method follows 5 principles. At first, the content recommended to users should be the most interesting one in 360 video. When users are watching the main normal field of view video, they should also be aware of the off-screen important content by referring to the candidate normal field of view thumbnails. Furthermore, virtual cameras are required to record different parts which share the minimal overlap. And the content users are watching should be stable. The transition to other candidates' views should be smooth enough. Last but not least, the transition should be efficient and users won't get lost. Given a 360 video, our method computes the saliency, optical flow, and instance segmentation during preprocessing. Then a dynamic programming-based optimization algorithm with a coarse-to-fine strategy is adopted to calculate the given number of camera passes. Finally, the results are shown in our user interfaces. The default video aspect ratio is 60:9. During preprocessing, in order to improve the computational efficiency, we uniformly resize the input video to a width of 360 pixels and set every 4 frames to 1 keyframe. Then the saliency, the optical flow, and the object segmentation maps are acquired by using the existing methods. First, let's consider how to compute a single camera pass. We just need to minimize this energy formula. The left term is for saliency and the right term is for velocity. PT represents a 2D pixel coordinate as the TIS keyframe. We can convert it to the formula below, which can be optimized recursively. It represents the energy of a pass from the first keyframe to the TIS keyframe ending at PT. For the TIS keyframe, we'll use the value to update the neighborhood at T+1 keyframe and record the best pass. It can be extended to multiple camera passes as shown on the right. We'll accumulate the energy of every camera and consider the interaction effect in the saliency term by using intersection over union for every 2 cameras. This animation shows the computation process of multiple camera passes. Please refer to our paper for more details. We offer 2 interaction interfaces. On the left, the candidate video thumbnails are shown horizontally below the main view. On the right, the candidate video thumbnails are floating on the main view by using outside-in method. Users can transition between contents by pressing direction keys or clicking thumbnails. We recruited 15 participants to evaluate. The results shows that our 2 interaction modes are better than others in locating capability, ease of use, and intention to use both in static scenes and dynamic scenes. Our method also has limitations. First, due to the limitation of memory, our method can process at most 4 camera passes. But according to our experiments, generally it is enough to cover the important parts in 360 video. Also, large number of cameras may lead to large overlap of field of view, which can degrade the view diversity. Second, the field of views of our cameras are fixed, which means if the tracked object is far away from the camera, it might be too small to observe the details. Finally, only saliency, optical flow, and instance segmentations are used for content awareness in our method. If extra semantic information are considered like human-object interaction, it may improve the quality of content awareness. Here, we show more interaction examples. Thanks for watching.